All right, let's start that. Now that the person who wasn't going to be late was late, but here. All right. So, refresh ourselves from the last two lectures. Probably shouldn't erase that. 2 lectures ago, we talked about the grammar that we were using to represent the logical form of any statement. And the grammar always consisted of these 5 things. All the symbols we drew were either sentential connectives, parentheses, terms, where terms are constants, variables, operators, or any combinations of those things. And then predicates and quantifiers. So the typical statement we worked with in that lecture, the one that we slowly build up from, is everything is read or not read. We said the way that we symbolize that is for all x, r applies to x, or not r applies to x. And that was the basic one we did, and then we did a ton of examples with more complex statements, breaking it up into these things. In here, let's say what everything is. Obviously, that's a parenthesis. The for all symbol there, that's a quantifier. X there is a term. Parenthesis, parenthesis, r is a predicate. X is a term. Or is a sentential connective. Not is a sentential connective. R is a predicate. X is a term. And then parenthesis is a parenthesis. That's what we mean. All the symbols I draw when I get at the structure of a sentence will fall into one of these 5 categories. Let's look at a typical math statement. For all x and for all y, x plus y is equal to y plus x. Still follows it. Obviously, parentheses are parentheses. We'll ignore those from here on out. Quantifier, term. Term, x plus y is a term. It's a combination of variables and operators. Equals is a predicate. If I give it 2 things, then it's true or false. You can say 2 equals 3. Is that true or false?
Yeah.
Yes.
It's a predicate.
So it's a predicate.
Input terms and output boolean.
We'll have more to say about identity later. Identity is very special. And it has a special place in logic. But for now, we'll just think about it as a predicate.
Okay.
And then y plus x, that's another term. So everything we represented here came into one of these 5 categories. That will always be the case when we now take statements and we break them up into their logical structure. We'll be breaking it up into those symbols and nothing else.
Could you give an example of constants? Looks like all these are variables.
Yep. For all x and for all y, x plus 0 is equal to 0 plus x. 0 there is a constant, x plus 0 is a term.
Okay.
How do you know that, is it because it's a capital letter that it's a...
As a general rule, we will typically use capital letters like R and P and whatever else to represent predicates. And we will typically use lowercase letters at the end of the alphabet to represent variables like X, Y, and Z. And we will typically use lowercase letters at the start of the alphabet to represent constants like A, B, and C.
Now,
Or, if it's understood from the domain we're talking about, we'll use, like if we're talking about numbers, we can use actual numbers.
wait, so is it the A, B, and Z that are constants? Is that what you're saying?
A, B, and C we typically use to represent constants.
Okay.
X, Y, and Z we typically use to represent variables. Capital letters we typically use to represent predicates.
Now, Rx is a predicate R with an input of X.
Correct.
Okay.
And the way that's often written is more like this. R parentheses X to remind us that X is being passed into R.
And we're just going to assume that that's always the case.
We can write it that way if we want. Sometimes it just gets tedious when you're doing a lot of them. But we could pass in, if over here, notice that plus makes sense here, right? I could rewrite this exact same thing as this way. This is a perfectly valid way to write it. For all x and for all y equals, applies to, x plus 0, comma 0 plus x. This takes those two things in.
In this case, the equal sign would be a predicate symbol.
The equal sign would be a predicate. We're just used to seeing equals written with this infix notation.
Yeah.
Which is a way that we sometimes write predicates when they take two terms. So in our axiomatic system last time, we said xqy. We could have just as easily said qxy, or we could have said qx comma y. And those are all equivalent notations, and you just kind of do whatever seems to make the most sense in the context. But to some extent, it's just a matter of convention or a matter of preference.
And you wouldn't consider it a grammar for like a function where you input terms and output terms. Is there any? How would you handle that situation in logic?
A function where you input terms and output terms.
Mm-hmm.
You can kind of think about a predicate as a function.
But it outputs a Boolean.
But it outputs a Boolean. Oh, inputs terms and outputs terms. Like an operator, you could think about plus as a function.
Oh.
Plus takes two numbers, it can take 1 and 3. And when I pass 1 and 3 into the plus function, it spits out 4.
Makes sense. Okay, so in programming it would be called a function, but you could actually call it an operator, and that symbol of the operator could be capital X or something, or capital R.
Yes. So an operator, but keep the distinction clear. An operator takes terms and spits out terms. A predicate takes terms and always spits out a Boolean, true or false.
That's more clear. Okay.
Huge difference. We use operators in constructing terms, and that's completely separate from predicates. Predicates are their own thing. So two separate things. Okay. Now we talked a lot last time about our axiomatic system. Over here. We talked about the system with two axioms and two definitions. Real simple system. Q here, to give an interpretation to it, Q meant weak preference, weakly preferred. And the way we thought about it is talking about foods to help us keep it straight. XQY means I'd be willing to eat X over Y if you think about it in terms of food. I weakly prefer X to Y. If we think about it in terms of food, that means I'd be willing to eat X over Y. So if you be willing to eat steak over a hamburger, you weakly prefer steak to a hamburger. If you'd be willing to eat a hamburger over steak, then you weakly prefer a hamburger to steak. So axiom 1 was saying, if you weakly prefer X to Y and you weakly prefer Y to Z, then you weakly prefer X to Z. If you weakly prefer a hamburger to steak and you weakly prefer a steak to a salad, you weakly prefer a hamburger to salad. Our second axiom was, for all X and Y, you either weakly prefer X to Y or you weakly prefer Y to X. Either you're willing to eat the steak over the hamburger or you're willing to eat the hamburger over the steak. Those were our two axioms.
So another way to look at that would be if Y is less than X and Z is less than Y, then Z is less than X. But that would be a way of quantifying.
That would be an interpretation. But then this one doesn't hold. Because it is not the case that X is less than Y or Y is less than X. So, what you said is another interpretation. It's just an invalid interpretation.
Yeah.
Okay. Now we create a definition in the system. This was some set of axioms that we thought might be useful for like psychology or something, where they wanted to talk about preferences, things people prefer to other things. And we said something that they might be interested in is the notion of indifference. If you're willing to eat the steak over the or if you're willing to eat the steak over the hamburger, and you're willing to eat the hamburger over the steak, if you weakly prefer the steak to the hamburger, and you weakly prefer the hamburger to the steak, then you're indifferent between the two. So we came up with a new symbol. For all X and for all Y, XIY, and the way we interpret that is indifferent. You're indifferent between X and Y if, and only if, you weakly prefer X to Y and you weakly prefer Y to X. If you'd be willing to take over X over Y and you'd be willing to take Y over X, then you're indifferent between the two.
I need a clear definition of weakly in this case.
Doesn't have a definition. So let me get to our last definition, then I'll have more to say about the axiomatic system. Finally, we have the notion of strong preference. We strongly prefer x to y, means we do not weakly prefer y to x. So if I strongly prefer steak to a hamburger, I am not willing to take a hamburger over steak. Make sense? So I was just giving you intuition for an interpretation up here. Now this here is what we call an axiomatic system. Every axiomatic system, I told you, is composed of four things. One, it has what we call the undefined terms. What are the undefined terms? These are the predicates and operators in axioms. So in this system, we do not define what Q is. This system up here, these axioms, there were no operators here, just a predicate. The only predicate that showed up in these axioms was Q. Q is undefined. We do not have a definition for Q in this system. The second thing we have in axiomatic systems are axioms. Probably should have put that as the first thing we have. That way, 2 makes sense. 1, we have axioms. Our basic assumptions, our basic premises, the things we assume are true. 2, we have undefined terms. Those are the predicates and operators that show up in our axioms. 3, we have our definitions. Our definitions we define in terms of our undefined terms. So notice, when I create a definition for I have to define it in terms of Q. When I create a definition for P, I have to define it in terms of Q. Now I could have came up with new symbols I defined, new predicates I defined, but I could only define it in terms of I, Q, and P because those are the only things I have in my system. It doesn't make sense in my system to suddenly say R is logically equivalent to M, R of X is logically equivalent to M of X and Z of X. Because M and Z aren't in our system. We don't know what those mean.
Others are.
M and Z?
I said neither is R.
Neither is R. I was trying to define R. I'm going to define a new symbol. Right? It's like trying to come up with a new English word, blah, and I'm going to define it in terms of ta and da.
I see that.
Right? Doesn't make sense. Now, why do we have to have undefined terms? Why can't we define everything? I tried to give you intuition for this last time. Why can't we define everything?
Because it goes in a loop. Circle.
Yeah, one of two things is going to happen. So imagine, let's pretend that you don't know any French. And I say, don't worry, I'll teach you every French word. Here's a French dictionary. You're going to have a problem. You look up the first word in the French dictionary, and what's it going to give you? A bunch of French words. So it defines French words as terms of French words. And if you go look up all of those French words, what are you going to find? More French words. And if you go look up all those French words, what are you going to find? More French words. And you're going to end up with one of three things. Either you eventually get back to one of the words you were trying to define. So they say, when you're looking up word A, they use the word B. When you're looking up word B to give its definition, they use the word C. And when you're looking up word C to get its definition, they go back and use the word A. It becomes circular. One dictionary did this once. They defined a mountain as smaller than a hill, and a hill is larger than a mountain. So I want to go find out. I'm learning English. What's mountain? It's something smaller than a hill. Oh, what's hill? It's something bigger than a mountain. Oh, that doesn't help. So this is one thing that can happen. You can get circular definitions. We don't want that in math. The second thing that can happen is your language is infinite, and there's an infinite regression to infinite words. Well, we don't want that either. The third possibility is you go back to a word that has no definition. And in terms of our axiomatic systems, that's what we do, and those are going to be our undefined terms. Now, just because it doesn't have a definition, does that mean it has no meaning? Does that mean it's a meaningless term? No, it's given meaning by its axioms. What is Q? It's something that satisfies this and this. That's what Q is. So you can't ask for a definition of Q. Doesn't make sense. To give you a more concrete example, in geometry, point is an undefined term. You can't define point. You can't define line. You can't define plane. And the axioms are what give them meaning. So, the third thing we have in every axiomatic system, or potentially have, is definitions. You don't have to have definitions. We could do a find and replace in all our proofs, and every time we see x, I, y, replace it with this, and all our proofs would still be valid. So you don't need definitions, they're just a nice to have. And they just potentially capture a nice notion. And then finally, the most crucial part of every axiomatic system, number 4, is
Connectives to grammar.
theorems, the things we prove, the logical implications of the axioms. And so last time, we introduced this axiomatic system. We had 2 axioms, 2 definitions, and we proved a bunch of theorems that followed from these things.
Yeah,
So, let's go back and just do the first theorem that we proved last time. So I'm going to reprove this in this system. You with me? Alright, so 1. What's the first line of my proof?
assume axiom or definition.
We'll start by listing out our axiom that we're going to use,
What you call it, proposition?
which is for all x and for all y, xqy or yqx. That's our premise.
Premise.
And that's axiom 1.
Mean and?
Or sorry, that's axiom 2. I just rewrote that.
Oh, okay.
It's dependent on itself.
It's only dependent upon itself. Oh, that's what you're saying. And it only depends upon one itself for its validity. In other words, line 1 is valid if line 1 is valid. Okay, next what do? We do universal specification. The new rule we introduced, was that last time or the time before?
That was last time.
Oh shoot. New rule from last time. You're in trouble if you didn't rewatch the lecture. You need to watch it. Universal specification. Since it's true for any x and y, it's true for an arbitrary x and y. So the x and y I'm going to choose for this are x and x. Those are symbols I'm going to use. So I now know that xqx or xqx. That's using universal specification on line 1, and it's still only dependent upon line 1 for its validity. Now, xqx or xqx3 is tautologically equivalent to xqx. This is tautologically equivalent to 2. If I know x or x, I know x. Right? We do that as a separate truth table if we need. I don't know if we specifically proven that one yet, but I think it's obviously true. And so, this is just dependent upon line 1 for its validity still. And now, since none of the variables are flagged, and you watched last lecture so you know what that means, we can universally generalize on this. And so we can rewrite this as, for all x, xqx.
Oh, it's not complicated.
Oh, it's not? Oh. Sorry. Thank you. Okay. Next, 4. We can get from this xqx and xqx. If you know A is true, you know A and A is true. Right?
Yep.
So this is tautologically equivalent to line 3. Still dependent just upon 1 for its validity. Okay, now, I forgot to introduce this as a premise, should have stuck it higher in the proof. 5, we introduce as a premise that for all x and for all y, which one is it, this one?
Yeah.
x indifferent to y is logically equivalent to xqy and yqx. And that now is a premise, and it's just dependent upon itself for its validity. Now we do universal specification on this, and so we get xq xix is logically equivalent to xqx and xqx. That is tautologically equivalent to line 5. This is still just dependent upon 5. And now I combine line 4 and line 6. This is logically equivalent to this. We have that right there. Putting this together with this, we're able to conclude 7 xix. This is tautologically implied by 6 and 4. And so now we're using premises 1 and 5 in our proof. Oh, sorry, this isn't tautologically equivalent to 5. This is doing universal specification on 5. Universal specification is how we get rid of our universal quantifiers. All right, and now we have xix. So line 8, now we do universal generalization. Since x is not flagged, we can say for all x, xix. That's using universal generalization on line 7. And that was only dependent upon 1 and 5 for its validity. Right?
I can't quite remember the rules for universal generalization. Is it just like if there's one variable left in what you're working with, then you can apply it?
You can apply it as long as the variable in there is not flagged. A flagged variable is a free variable introduced in a premise. So where the x here, where is the premise that introduced it? This did. And it wasn't a free variable because it came with these quantifiers.
Okay.
And the x that we used here, where was it introduced? In this premise. And it wasn't a free variable because it was introduced with those quantifiers.
Okay.
So I couldn't just randomly in this proof introduce something like, hx is a premise, and then say, therefore, 10 for all x, hx. Because then I could combine both those together using conditional probability to get rid of that as a premise, using conditional proof to say hx implies for all x, hx, which is not a true statement. So the reason that we can go from here to here is because of the rule that you can't do it when it's a flag variable. That would be a flag variable since I introduced it as a premise.
Do we have a way of notating whether it's a flag variable, or do we just have to remove
Yes, we do. When I introduce it, so if I did introduce this as a premise, over here when I wrote my set, I would have written 9x, like that. So I put the flag variables after the line number that the premise is introduced on.
Okay.
And then every time I write after that, it'll be 9x, 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 until we get rid of it. And you'll see me do that a lot. We did a ton when we were proving these. Because it's commonly the case that you introduce a flag variable, but you get rid of it before it's all said and done when you get rid of the premise. And then you generalize. Anyways. So for this proof, there we go, we proved it. Now, when we're working in an axiomatic system, I don't ever want to have to rewrite my axioms. It's understood that we're assuming these things are true. So rather than adding as line 1, just restating our axiom, we'll typically jump straight to this line, and we'll say that this is universal specification on axiom 2. And we'll instead say, and this depends on its validity for axiom 2, axiom 2, axiom 2. And then we wouldn't have line 5 in here. And instead on this line, we would say that's universal specification on definition, was that definition 1 or 2?
2,
1.
1.
And then so we would put a D1 here, and then these would have been A2, D1, A2, D1. And so this conclusion we know is true, and it's dependent upon its truth. It's dependent upon axiom 2 and definition 1 for its validity. So if this is true and this is true, then we can conclude this. That's what we call a theorem. The conclusions that we can come to based off of our axioms and definitions if our theorem uses the definitions. And we proved a bunch of theorems after that. Now we're going to switch to a new axiomatic system. We're going to switch to the one I have listed here. Get a little bit more complex. So this time we're going to work with an axiomatic system. This time we're going to have 5 axioms. No definitions this time though, because it's already got plenty of symbols. So 5 axioms, no definitions. And notice up here we didn't have any operators. Down here we're now going to have operators. So let's get as comfortable with each of these, each of our undefined terms that we use in our axioms. Our undefined operators and predicates. We're going to have the predicate C. C takes a single term. You with me?
Okay.
So it's a one-term predicate, like is blue. Is blue can only take one term.
What's an example of a two-term predicate?
Last line. Last line you need 2 terms.
Oh, I see what you mean. Okay.
Loves. Loves you need 2 people. You need to say X loves Y.
Right, so it's X.
So that would be a 2-place predicate. So C is our only predicate and it's a 1-place predicate.
Okay.
We have 2 operators. We have plus. This has nothing to do with arithmetic. It's just a symbol. Plus is an operator. It takes 2 terms. So if I do X plus Y, that's perfectly valid. That's 1 term. X plus Y is a term. I could then plug X plus Y into C. And we'll use parentheses now when we plug it in, since it might get messy while we're plugging into C. Our other operator is going to be prime. This is a unary operator. It only operates on a single term.
Like the C.
Like the C is a predicate that only takes 1 term. This is a unary operator. So I can say X prime, and I can prime my X.
I don't understand that.
A unary operator,
A union operator?
unary, 1.
Oh.
Not binary, unary, 1. Square root is a unary operator. You give a number like 9. And now it's without 3. Reciprocal is a unary operator. 3 to the minus 1 is 1/3. That's a unary operator. Okay? So it's a unary operator. So X is a term, X prime is still a term. If X is a term and Y is a term, X plus Y is a term. We can plug our terms into C. So I can plug X into C, I can plug Y into C, I can plug X plus Y into C, I can plug X prime into C. I can plug X plus Y, all prime that, plus Z, all primed again, into C. I can plug all that into C. Still just a term when it's all said and done. Make sense?
Yep.
Good? Okay. This time, working with hopefully what's a more complex system. 5 axioms. Here's our undefined terms. C, plus, and prime. Those are the predicates and operators that show up in our axioms. They have no definition. What gives them meaning? The axioms.
So what does C mean?
Doesn't mean anything.
Like Q did.
I gave you an interpretation for what Q could mean up there.
Okay. That was just because.
Yeah, that was just to help you get comfortable with it. Now the point of this example is to give you something where you're hopefully not comfortable with it. Hopefully you don't like that you don't know what C is and you don't know what plus is and you don't know what prime is. And that bugs you. And I want you to prove things with it, even being clueless as to what these things mean.
Okay.
And then when it's all said and done, I'll give you some nice intuition for how you can think about each of them. And you'll say, oh my gosh, why didn't you say that in the beginning?
Okay.
But first, let's fight it. And get comfortable. Because this is what you do as you get deeper into math. You need to get comfortable just thinking about just what the axioms give you. Forget your intuition, leave your intuition at the door. It's going to mislead you, it's going to misguide you. Throw that out at the door. And just think about exactly what you're given. And then reason about exactly what you're given. So this is exactly what we're given. These 5 things. And we're going to reason about each of these 5 things to come to these 11 conclusions. So let's read through each of these.
Yeah, second one looks wrong.
For all x and y, if you know c of x plus y, then you know c of y plus x. Okay, that one seems okay. This one. For all x and y, if c of x is true, then c of x plus y is also true. Again, this has nothing to do with addition on the real numbers. All right, next one. For all x, if c of x prime is true, then c of x is false. Or not c of x is true. This one says for all x, if it is not the case that you have c of x prime, then you have c of x.
It's just trying to define C.
It's not trying to define anything.
You're trying to like create the rules of what C is.
Yes, this is giving the rules for what c, for what prime, and for what plus are.
Interesting.
What are c prime and plus? C prime and plus? They are the 3 things that operate according to these 5 rules. That's what they are.
That's interesting.
They have no definition. Alright, and finally the last one. For all x and for all y, if you have c of x plus y, and you have c of x prime, then obviously you have c of y. Right?
Yep.
Okay, let's start proving these. So let's prove the first one. Let's start by trying to prove that one. If you don't have c of x, then you have c of x prime. That's what we're trying to prove. Where might I start with this? Go ahead.
Real quick, what's the difference between definition and a theorem?
What's the difference between a definition and a theorem? A definition is introducing some new symbol.
Oh, that makes sense. Yeah.
And it's introducing it in terms of existing symbols. Theorem is a logical conclusion, is a logical implication of your axioms and definitions. You can think about a theorem is really just a logical implication of your axioms because you never actually need to use your definitions. I can replace the I there with xqx and xqx
Like as if you
and get rid of i's altogether.
As if you take a definition of a word and replace that word with the definition type of thing.
Kind of. Or to think about in terms of programming, when you define some new function and you use it in a place, you didn't actually have to use that function. You could have just reinserted that logic right there and redone the logic.
Exactly.
So the definitions, it's like a way of packaging some logic up together in a nice little symbol so that we can use it more efficiently.
And so okay, so a theorem is like trying to prove something, or
A theorem is a logical implication of your axioms.
I don't quite understand the term logical implication.
We know this is true if we know that these 2 things are true. If these 2 things are true, then this must be true.
Okay.
Its validity, it is valid if these 2 things are valid. This depends for its validity just upon these 2 things. All these statements we prove here depend upon for their validity, just these 5 statements.
So if it's okay, so the theorem is trying to prove the axioms, or is the theorem?
There is no proof for the axioms.
Uh,
A proof means I show. So when I show a theorem is true, what do I show? I show that the axiom, so if I have 2 axioms, I show axiom 1 and axiom 2 implies my statement, my theorem, I'll call it T, implies T. I show this is true. That's a proof.
You're proving the axioms. Or is the
No, I show that the axioms imply my theorem.
So the axioms are proving the theorem.
The axioms are our initial premises. These are our axioms.
Yes.
This is our theorem. A proof is showing that these imply this. Maybe it doesn't imply that. Maybe you can't prove it.
Okay, so we just assume that all the axioms are true. And then we use those axioms to prove all this other stuff.
Correct.
Which I know we talked about a lot. And so I'm making that connection. So a definition is just proving a new thing, using a new symbol to kind of like a function. But then a theorem is almost something you would build on top of axioms that are built on top of an axiom. Okay.
Yes, theorems are new statements.
But you can almost switch out a theorem at any point with it and just define it with a new definition. And
A definition is always introducing a new term. This isn't introducing a new term.
at any point
So here's a whole system where we never use a definition. So you don't need definitions. Definitions are nice to have for humans.
yeah.
They just give us shorthand notation. Theorems are the logical implications of your axioms. So Euclid's Elements, he has 5 postulates, 5 axioms. All 13 works of Euclid's Elements are saying, if these 5 axioms are true, then all these theorems are true. He says, look, if this axiom is true, and this axiom is true, then this statement over here is true. And if this axiom is true, and this axiom is true, then this statement's true.
This theorem,
This theorem. So these are theorems.
right?
And then if this theorem's true, and this axiom's true, that gives us a new theorem.
Are theorems and statements interchangeable?
A theorem is always a statement.
Okay. Okay, that's good. It's becoming big for me.
Okay. So, let's prove this theorem of these axioms. We need to show that these axioms somehow imply this theorem. Alright, so where might we start?
Universally generalizing A4.
Axiom 4. What's he noticing here? He's saying A4 is almost the exact same thing as this.
Isn't it universal specification?
Yeah, it's universal specification.
That one,
When we go from the general to the specific, that's universal specification. And then when we add the quantifier, that's generalizing. So we're going to start out with, right here, I know that not C of x prime implies C of x. This is universal specification on axiom 4. It depends just upon axiom 4 for its validity. Right? Okay, now what?
Forget the term. It's like I contradiction or something like that.
Contrapositive.
Contrapositive.
Now we write the contrapositive of this. Remember, if alpha implies beta, then we know not beta implies not alpha. So if this implies this, then not this implies not this. Right? So number 2 is not this implies not this. So that's tautologically equivalent to line 1. And still just depends upon axiom 4 for its validity. Right? And now, not, the nots undo each other. So this is the exact same thing as not C of x implies C of x prime. This is tautologically equivalent to 2. We still just depend upon axiom 4 for our validity. Now what?
Universal generalization?
Universal generalization, 4. So now we can say for all x. If it's true for any arbitrary x, then it's true for all x. not C of x implies C of x prime. That is universal generalization on
And 3.
line 3. And that depends upon, for its validity, axiom 4.
Square box.
Square box, we're done. Thus it is demonstrated. So we just barely showed, if axiom 4 is true, then theorem 1 is true. Because theorem 1 only depended upon, for its validity, axiom 4. This is what we mean, axiom 4 ultimately implies theorem 1. Good? Alright, let's do the next one. Theorem 2. What are we going to start with for theorem 2?
B3.
Yeah, basically the same thing.
Axiom 3. Yeah, we're basically doing the exact same thing with here. So we do universal specification on axiom 3. So that gives us C of the variables that we use here are completely arbitrary. Just to shake things up, I'm going to say universal specification on axiom 3 gives me that C of z prime implies not C of z. If it's true for any x that this is always the case, then it's definitely true for an arbitrary element z.
Are we going to do existential next week or next class?
Yes. So again, this was universal specification on axiom 3, and we are dependent for our validity just on axiom 3. Right? Now what do we do?
Contrapositive?
Contrapositive. Not this implies not this. So not this is the same thing as C of z implies not this. Not C of z prime. And this is tautologically equivalent to this, so we're still just dependent upon axiom 3. Right? And then we universally generalize. Therefore, for all z, C of z implies not C of z prime. And it doesn't matter that this is a different variable than what we have written over here. It's just a variable, a placeholder. You can call it x, you can call it y, you can call it z, call it whatever you want. Okay, that's that one.
Did you mean to make that an equivalence then? Because we only proved one way. I guess axiom 4 is the other way of the implication.
Oh, is that logically equivalent? I think that might be my own thinking in my head and not the way it was written there.
It doesn't make sense.
It's true that they're logically equivalent,
Oh, it does make sense.
but no. This is just supposed to be implies this way, following what the book has. Okay. Next one. Theorem 3. Let's prove this one. All right, what are we going to start with for that one?
A1.
Universal specification on A1.
Theorem 3, universal specification on A1. So I'm going to write it a bit different. Hopefully you guys can see this. Okay. We're looking at A1, universal specification.
Yes.
So I'm going to write C of y plus x implies C of x plus y. In my universal specification, I'm choosing to replace the x variable with some random variable of my choosing. I chose y. And I'm choosing to replace the y variable with some random variable of my choosing. I chose x. All that matters is, if I substitute my x with the symbol y, I have to replace all my x's with y's. And if I choose to replace my y with an x, I have to replace all my y's with x's. So that was a valid way to plug in there. I could not have replaced that with an x, that with a y, that with a z, and that with a w. However I substitute one symbol, I have to do it for all. As long as we do that, we're good. Okay, and so this was universal specification on axiom 1, right?
Yes.
I'm going to stop writing the rule, and I'm just going to go straight to, we're using axiom 1. I think you guys can follow it. Okay, next one. Contrapositive. 2. Using contrapositive, we know not this, not c of x plus y, implies not c of y plus x. Right? And now what? Universal generalization on this. And then we get an identical thing. Cool. Let's move on to the next one. Next one, theorem 4. Some of these markers are really pulling up for me. Try blue again. All right, theorem 4. What might we start with?
A5 universal specification.
You're saying which one?
A5.
A5 universal specification. What you're doing can work. So she's going to do universal specification on this, then manipulate this whole thing as we go until we get it into the form we want. Perfectly valid way to do it. Once these things start getting too messy, we can go back to our standard way to always prove an implication, in case it feels like it's getting too messy. So I'm going to go back to our standard way that we always prove an implication, even though what you're saying would work. How can we always prove an implication statement?
Assume the first part and then show it.
Which one are we proving? Theorem 4. How can we prove an implication? Assume the antecedent and show that implies a conclusion. I could have done that in proving theorem 1, theorem 2, theorem 3, but those ones were kind of simple enough that you could just see it all in one go, and we didn't need to break it up that way. This one's getting big enough that maybe it's justified to break it up some. And then this will also show us 5 variables, which is another reason why I do it. That is not writing well. Is anything beating that black? Shoot. Should have brought my own markers. Okay. I keep forgetting what we're proving. 4. So, 1, I'm going to introduce as a premise, and it's a premise that I promise I'm going to get rid of. The antecedent. So I always indent when it's a premise I'm going to get rid of to remind me. So assume the antecedent, x plus y, and not c of x. This is a premise. It depends upon for its validity itself, 1, and it has the flagged variables x and y in it. So I do 1, and then I do x, y. Right? Okay. So there we go. We introduced it as a conditional premise. Okay. Now, what do I want to do? Ultimately, I want to replace that not c of x with a c of x prime. Because then we can conclude c of y, which is what we're trying to get. Remember, I'm trying to show theorem 4. I'm trying to show this being true implies this is true. So I'm starting with this, and I'm trying to get dot, 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 dot down the line somewhere. I'm trying to show c of y.
Okay.
So that's my starting point. So if I can get this to be a c of x prime, then we're there. Right?
Yeah, and that's easy with A3.
Right. I know from theorem 1, I know not c of x implies c of x prime. And this is theorem 1.
I see.
And it depends upon for its validity. Whatever theorem 1 depended upon for its validity.
What are we gonna write then?
So I don't remember what theorem 1 was. Was it axiom 4? We won't actually do it this way.
Yes.
So axiom 4.
I believe that's what it was here.
So this is one way we could do it. That's being more proper about it.
What are we gonna do?
We're just going to use theorem 1 all in one go. So notice that theorem 1 tells me that not c of x implies c of x prime. So I'm just going to go straight down to 2 we have c of x plus y and c of x prime. This is tautologically implied by line 1 and theorem 1. And we don't need to keep track of what theorem 1 was dependent upon for its validity, because we already know it was the axioms. So we're not worried there. We know that that already falls from the axioms, so we're good there. So we can use that theorem in our proof. And that's the nice thing about proving theorems. Later proofs, you can use previous proofs. Perfectly fine. And you don't need to redo all the logic.
It's a lot like just a definition.
Kind of. Okay. So now we have that. Now what can we conclude?
We can conclude C of Y.
I'm going to go straight to using C of Y.
What, A5?
Rather than rewriting out axiom A5, using universal specification, whatever, we're going to skip straight to just thinking about it. I know that this implies this from axiom 5. So this is tautologically implied by 2 and axiom 5. And so now we're dependent upon for our validity 1, xy, and axiom 5.
But now we can't do.
But we can't do universal generalization yet.
Yeah.
But now we can use conditional proof. And we can go to, therefore, this implies this. So we can now say C of x plus y and not C of x implies C of y. That's using conditional proof. And that's how we get rid of our premise. And so now we got rid of 1, xy as a premise. So conditional proof from lines 1 to 3. And now we no longer have 1 as a premise. And so now we're just dependent upon for our validity A5 and theorem 1. You can keep track of theorem 1 over here if you want to remind yourself, but I'm not going to bother.
In the example, it was like h of x or something. You did this exact thing and said it wasn't valid. You introduced h of x as a premise and then.
Let's redo what I was doing over there. 1, premise. H of x. This is a premise. Depends upon for itself. 1 is a defined variable. 2. For all x, h of x are cheated. That's
Oh,
universal
okay, I see.
generalization. Depends upon itself, 1x. Then we might say 3, therefore h of x implies for all x, h of x. And that doesn't depend upon any premise, so we can conclude that in general.
Mm-hmm.
No, because the cheat was here.
Okay, that makes sense.
Yeah, so we do remove it as a premise, but too little, too late. That's bad proof. That's a cheat. Can't universal generalize on a flag variable. Going from here to here, we got rid of the flag variable. We are no longer dependent upon premise 1 for our validity.
So using
So we no longer have a flag variable, so now we can universally generalize this, which is exactly what we were trying to prove.
Square box.
Square box. Don't want to waste my ink. My marker's dying. Okay. So that was showing you flag variables. And if you can't think about how to do it any other way, anytime you're proving an implication, you can always start by assuming the antecedent. And that's typically the way we start all proofs anyways.
okay. You're 5.
Theorem 5. Alright, theorem 5, what are we going to do?
We're gonna have to use
Assume the antecedent.
Probably start by assuming the antecedent.
use that one,
Safe place to start. So we do 1, we assume our antecedent is indented because we got a promise to get rid of it, not C of x plus y. Right? And x and y right now are flag variables. We can't universally generalize on that. We gotta get rid of it as a premise before we universally generalize. Alright, 2. Now what can we conclude?
Well, I guess using the contrapositive of A2, we can prove not C of X. That's one part of the and
Sure.
statement that we're trying to prove, I guess.
Oh yeah, there we are, I see that.
This right here is axiom 2 says C of x implies C of x plus y. Where the contrapositive of that is not c of x plus y implies not c of x.
Oh, and we can use the same thing for y.
So we can say, therefore, not c of x. This was the premise. This we can conclude using axiom 2.
Mm-hmm.
Yes.
Okay, now what?
And you can do the same thing for y, just switch the variables.
How can we switch the variables?
You do it. You said you could. You said x
Oh,
minus
from
2.
theorem 3?
From theorem 3,
If you universally generalize.
you have to be careful that you don't assume too much. Maybe we shouldn't have used a plus symbol. Because addition, it turns out, on the real numbers, addition happens to be commutative. You can swap the order. That doesn't mean that the plus symbol we have here, you can do that too.
You said that in A1 though.
No! What did we say in A1? We said that c of x plus y is true, then c of y plus x is true.
Oh, they're not equivalent.
This is not c of x plus y is true. And what Anna says is right. We prove this as a theorem. Not c of x plus y implies not c of y plus x. So we are able to come down here and say 3, not c of y plus x, but we're using theorem 3 as our justification for that line. We couldn't just say it,
Okay.
right?
Where does that get us?
Where does that get us?
Not c of y.
Now we can conclude not c of y. Now we can conclude not c of y using axiom 2 again. What does axiom 2 say? It says if you don't have the contrapositive of this. So let me rewrite the contrapositive of this right here really quick. Contrapositive of this is not c of x plus y gives us not c of x. Right? Sorry, maybe my C there looks a little funky. Probably should have used an F or something instead of something that looks like parentheses. This is a contrapositive of this, right?
Okay.
So if you don't have a term plus a term, then you don't have C of that first term.
Okay.
So if I don't have this plus this, then I don't have this. If I don't have the sum of those two, then I don't have C of the first thing.
That's fair if you switched it around.
Yeah, the order doesn't matter.
And then you replace the x with y.
Yeah, we're replacing y's with x's and x's with y's.
Okay. Yep.
And that's valid to do. But we did have to do each of these steps. So we can't conclude not C of y. Because one interpretation of this sentence is, one interpretation of it would be, not C of y plus x implies not C of y. We're just relabeling the variables. We can always just relabel the variables. Doesn't matter what symbol we use to represent a variable.
They have to be constant throughout your whole proof, don't they?
Constants we have to be more careful with.
Well, the variables have to be the same throughout the whole proof.
We have to replace it the same way. If I replace this x with the y, I have to replace that x with the y.
Yeah, I see.
As long as I do that, we're fine. Because it doesn't matter what we call the variable, it's just a name for it. We can relabel it whatever we want. So this and this are identical. There's no difference between them.
Well, yeah. Well, yeah.
Because variables aren't predefined.
Yeah, it's just a placeholder.
Right.
It's like if you're programming some function and you call the first variable x and the second variable y, you decide, oh, actually, let's redo it. I may call the first variable y and the second variable x. As long as you switch all the x's and y's throughout the body of your function, you're fine. As long as you do it everywhere, you're fine. It doesn't change anything. It's just a name. Okay, so now we got that. So we just barely showed that, notice that we only depend upon axiom 2. So what's line 5? Line 5 is combining this with this. So we have, oh, sorry. We still need to remove that premise. So we have not C of x and not C of y. Right? And that's just combining lines 2 and 4. So it's tautologically implied by 2 and 4. Does that not feel super obvious? We introduced this as a conditional premise. So we said if it's not the case that you have c of x plus y, then you don't have c of x. That was the contrapositive on this one. Then we said if you don't have c of x plus y, you don't have c of y plus x. That was using this theorem. That's exactly what this theorem proves. And then we said if you don't have c of y plus x, then you don't have c of y. That's just reusing the contrapositive of this, just swapping variables. And so what did we show? We said if this is true, then you have this, and if this is true, then you have this. So if this is true, then you have both those. So we just really showed if not c of x plus y, then, did I put parentheses when I wrote over here? Yes. Then you don't have c of x, and you don't have c of y. And now 1 is no longer a premise that we're reliant upon. So if we would have been doing these, we would have had 1 here with x and y. Along the way, we would have introduced axiom 2. Down here now, we finally just have axiom 2. And we no longer have that as a premise. We removed it right here when we did rule CP to remove it. Our rule of conditional proof. That's our rule that enables us to get rid of a premise. So we got rid of this as a premise. And now I can universally generalize on this, which is exactly what we were trying to prove, right? Ready to move on to the next one, or still need to start it for a sec, or what? Just no?
I'm good.
Yeah, I'm ready.
Alright. Which one are we doing? 6?
We're on 6, yeah.
Alright, we're on 6. Okay, what are we doing with 6? We're trying to show that if you don't have c of x and you don't have c of y, then you don't have c of x plus y.
That's not. Okay.
Right? So this is just the converse of this. Not the contrapositive, the converse. Just flipping the implication around. We said this being true implies this is true. The other one saying this being true implies this is true, so these are somehow logically equivalent.
Yeah, that's what it means.
Alright. So, theorem 6.
Assuming antecedent.
Assume the antecedent. Pretty safe place to start. So 1. We have not c of x, and we have not c of y. That's premise. Depends upon 1, and we have 5 variables, x and y. Because they're free variables in the premise. Okay, now what are we going to do? Bang our head against the wall, bang our head against the wall.
The only thing I can think of is proof by contradiction.
That's exactly what I thought of too. So when you try to look at, I know not c of x, what does that tell me? And we start looking at all this stuff. And it doesn't seem like that there's anything we can do. Common times when you're trying to prove something, you just kind of get stuck. Where to go next? I don't know, you have ideas? We might not have to do it by proof by contradiction, I don't know.
I'm just thinking we could use it. No, we couldn't. This, no. Let's just stick with proof by contradiction.
So, in general, what happens is, you try to prove it, nothing's really working out. If you can't prove it, one of our fallbacks is, try and do it by proof by contradiction. When you just get stuck. And that's what I did. I tried to do it, couldn't think of a way to do it, I got stuck, I said, I'll just try proof by contradiction. Natural thing to do. So now we're going to introduce as another conditional premise. So we do another indent. We're going to assume, by way of contradiction, not our conclusion.
So C of x plus y.
I forgot where we were.
It's theorem 6.
Theorem 6, thank you. So here's our conclusion. So we're going to assume by way of contradiction, if we were writing out a math proof, we say assume by way of contradiction,
Yes.
C of x plus y. But we're just going to say that's a premise, and it's a premise that we're going to ultimately get away from. I do another indent to remind myself, I'm going to ultimately get rid of that as a premise to help me prove this, or to help me do what I was trying to do with this, and once I'm done with this, we'll remove that. Anyways, sorry, forgot my 2 here. 2. So this is dependent upon 2 for its validity, and it has 5 variables, x and y.
Okay.
Right? Okay, so now we need to get some sort of contradiction from this. Somehow this needs to contradict what these are saying. So if I know C of x plus y, what do I know?
C of y plus x.
We know C of y plus x.
We using theorem 1, we can get C of x prime.
Let me see. Let me make sure I did actually do that. This is theorem 6. Okay, yes I did. Alright, using what?
Theorem 1.
You're saying using theorem 1.
We can get C of x prime and then use A5 afterwards. I think that contradicts.
Using theorem 1. I'm not sure what you're trying to say there.
Using theorem 1 in our first line. Like the not C of x.
You're saying take not C of x to give us C of x prime.
Yeah, and then we can use A5 with line 2.
Okay, so you're saying, let's conclude C of x prime really quick. This is tautologically implied by 1. So now we're dependent upon 1 with its 5 variables and 2 with its 5 variables. And now you're saying combine.
I don't think we're dependent on 2 technically at this point.
Yeah, no, 3.
Line 3 is just dependent on 1.
Oh, thank you. Good point. Okay, now combining this and this, and using what?
A5?
Axiom 5. So this and this
That's wrong.
gives us C of y.
That what?
You didn't see that?
I did.
We have C of x plus y, and we have C of x prime. Axiom 5 says if you have C of x plus y and you have C of x prime, you can conclude C of y. So we're concluding C of y. This is tautologically implied by 2, 3, and axiom 5.
Okay,
Right? And so now we're dependent upon 1, 2, and axiom 5. Where 1 and 2 we can say they have 5 variables. Okay, now what?
Now we have a contradiction.
yeah.
Right, so now 5, we have C of y and not C of y. Because we have not C of y right there. So this is tautologically equivalent to 4 and 1. And it's dependent upon the same things for its validity. Contradiction. So then we can conclude line 6, not this. So then we conclude not C of x plus y. This is by rule reductio ad absurdum. And we did that from lines 2 to 5. And so now we are dependent upon for our validity just premise 1 and axiom 5.
Square box.
Not.
Yeah. What? Well, after you write down the actual
Right, so
question.
now 7 is this implies this. So now we're saying
I see.
not C of x and not C of y implies not C of x plus y. This is using the rule of conditional proof. And now we're only dependent upon axiom 5 for our validity. And now we can universally generalize. And we're done. Something weird?
You forgot to put your parentheses in. I don't know why it's bugging me so much.
You want that? Okay. And then we universally generalize and we're done, right? Any questions on that one? Okay. What number was that?
6.
6. Okay, so now we're on to theorem 7. Okay, theorem 7. Now things just got really weird.
No.
How are we going to prove theorem 7?
Well, 2 primes cancel out, so.
How do you know 2 primes cancel out?
With A3 and A4,
Yeah.
How do I start my proof of 7?
you would assume the antecedent.
What antecedent?
C of x prime x prime.
Oh, I didn't realize there were 2 arrows.
Yeah, it's a back and forth arrow. How do we do that?
Well, to do it this way, to do it to the right, you would assume the
Let's do both
antecedent was.
antecedents.
So we need to remind ourselves that alpha is logically equivalent to beta,
Alpha.
means alpha implies beta, and beta implies alpha.
See,
So if I want to show that two things are logically equivalent, I need to show alpha implies beta, and then I need to show beta implies alpha. So it's like doing 2 proofs in 1. So I need to show that this being true implies this is true, and then that this being true implies this is true.
so it's a long proof.
It's just 2 proofs in 1.
So it's just 2 proofs in 1.
Okay.
So we introduce as a conditional premise
Go and see again.
C of x prime prime, right?
Yes.
And then what?
Use A3.
We use A3. If you have C of a variable prime, you have not C of that variable. So I have C of some variable prime, so I have not C of that variable. Right? And then same logic again. If I have C of a variable prime, I have not C of the variable.
Not C.
C of x prime is not C of x.
Okay, yeah, I see.
And then that not just carries over.
Yeah.
Unless we already did a proof earlier for not C of x prime.
There's just
You
axiom 4.
Axiom 4, yeah.
Not like a proof, but it is the
Oh,
same
so we don't even need to do that. We can just use axiom 4. Axiom 4 says not C of x prime gives us C of x. So using axiom 4, we can go straight to C of x. So then line 4 would be the line where we use our conditional proof. And what did we show? We showed C of x prime prime implies C of x. Right? And then line 5 is like we're starting all over again with a new proof. Now we introduce C of x as a conditional premise. Now what might we do?
Use theorem 2.
We can use theorem 2 to get not C of x prime. So this gives us not C of x prime. That's using theorem 2. And now what can we do?
Theorem 1.
Theorem 1.
Theorem 1. Not C of some variable is the same thing as C of that variable prime.
That doesn't get us anywhere though.
So that gives us C of that variable prime.
What?
Not C of some variable gives us C of that variable primed.
Oh,
Not C of some term gives us C of that term primed.
I see that.
And then so line 8 here would be, we showed that C of x implies C of x prime prime. And so line 9 would be combining these two. So I have this and this. And then we use this logic here. So line 10 would be saying that C of x is logically equivalent to C of x prime primed. And then we universally generalize, because we got rid of both our premises. Introduce a premise here, got rid of it here. Introduce a premise here, got rid of it here. Since we got rid of both our premises with the 5 variables, we can universally generalize and we're good. Cool. Let's try the next one. Theorem 8. How are we going to prove theorem 8? Step 1,
Assume the antecedent.
assume the antecedent. Pretty safe.
Did you mean to write for all x and for all y instead of for all x twice?
Yes.
Would it be easier to assume the antecedent by contradiction of that? Would that like be realistic? Contrapositive, I mean?
Sorry, what?
Assume the antecedent of the contrapositive of that. Seems easier to start with not cy than all of that. Take theorem 8 and take contrapositive of that. And then you have not cy and then assume that.
You're saying prove the contrapositive of theorem 8 and then say therefore you have theorem 8?
Kind of.
You could do that.
It just seems easier to start with not cy than all of that.
I don't know why. This gives us more information to work with than this gives us.
Just thinking out loud, guys.
So my intuition is the exact opposite of yours. I might agree with you if we had it the other way. Then I'd say, let's look at the contrapositive. But that is a valid thing that we sometimes do. We say, I'm not sure how to prove this statement. Let me think about how I might prove it's contrapositive. And then we prove the contrapositive, and then we get the statement. And I think we even did that a couple times in discrete math.
Probably.
All right. So it is a valid approach. So 1, assume the antecedent. So we have C, we're doing 8, right?
Yes.
So we're introducing C of x and C of x prime plus y.
Yes.
And we're trying to include C of y from that.
Yes.
Okay. What are we going to do now?
Well, you can use theorem 7 to get C of x prime prime.
Use theorem 7 to replace C of x with C of x prime prime. And I'm also going to flip the order as I do this at the same time. Because and is commutative. Just to help you see where she's going with this.
Okay.
So now we have C of x prime.
What do you mean and is commutative?
You can and in any order you want. It doesn't change anything. Alpha and beta is the same thing as beta and alpha. So, and C of x prime prime. Is that the one we want to use? Maybe there's one that gives us a bit cleaner.
We can use A5.
Rather than that, I'm going to use theorem 2 and replace the C of x with not C of x prime. So this was using, this we had a premise, this is using theorem 2 here.
Oh, yeah. Okay. Now we can use theorem 4.
What did theorem 2 say? If you have C of x, then you have not C of x prime. So that's all I did, is I replaced my C of x with not C of x prime. So now, we know C of a variable plus y and not c of that variable.
Therefore, C of Y.
This right here says, if you know c of some variable plus y, and you know not c of that variable, then you know c of this variable. So this, we can use theorem 5, and we're just replacing our x's with x primes. Okay, so 3, then we're able to conclude c of y. And that's using theorem 5. And then conditional proof, saying this implies this, so we get rid of this as a premise, and then universally generalize.
C.
So we showed this implies this.
Yes.
Okay, that was theorem
8.
8. Let's do theorem 9.
Okay.
All right. Here's a weird one.
Yeah.
Where are we going to start with this one?
What I'm trying to get at.
We're trying to prove that for all x, it's the case that you have c of x plus x prime plus x.
X plus
That's
x.
always the case.
X plus x prime plus x is also just a term within itself, right?
Yeah. How do we start? We don't have an antecedent we can assume. Notice all our axioms are just implications. They don't really give us a starting point. See, in our earlier system, we had a nice starting point that we could always use. But yeah, all our theorems are implications. We don't have an antecedent we can assume. What can we do?
I mean, there's a way to turn implications into or statements. I'm not sure which implication we would do that on though. If you're looking for a nice starting point.
That's a thought. Reverse engineer some or statements, see if it gives us a nice starting point. You could try that. I tell you that you probably run into some headache doing that, but it's a thought. What else can we do?
I still don't.
If you don't know how to show it's true,
Don't know what we're trying to prove.
we're trying to prove this. It's kind of like, I'll give you a algebra equivalent. It's like I say, I want you to prove that for all x, x times 0 is equal to 0.
That's an axiom.
No, it's not.
Okay.
The axiom is for all x, x plus 0 is equal to x. This is not an axiom, this is something that you prove.
So we're saying for all x, C will basically return true.
For all x, it is true that C applies to x plus x prime plus x.
If you input x plus x prime plus x, it will return true.
Into C, it will always be true for any x you give it.
We can assume or prove by contradiction.
Proof by contradiction is a good way to attempt this. You say, I have no clue how to prove that thing true. What can we do? We can start with, let's assume it's false. That gives us a starting point. And then see if that leads to some contradiction.
Okay.
That's a perfectly valid way to do it. You can do it that way. Nothing wrong with that. Another way we can do it is we can start with some tautologies that we know are always true. We were doing number 9, right? So another thing I can start with is I always and forever know it's the case that we have for all x, c of x, or not c of x. Proof by contradiction says we always know it's the case that for all x, it is not the case that you have, it is not the case that you have c of x and not c of x. Well, not really specific to this. Going back to two tautologies that we always have, writing it just in terms of sentential connectors. We have the tautology that we always have alpha or not alpha. That's a row of excluded middle. When you do proof by contradiction, like Emma was thinking, that's in the back, that's indirectly using the fact that this is a tautology. Alpha and not alpha, all knotted. It is never the case that we have alpha and not alpha. So, proof by contradiction is using this tautology behind the door, or we could go and start by using this tautology. Either way works. So we can start with this and start working from it. So then I know C of x or not C of x. Maybe I'll write both approaches at the same time, just so that we can see them both. So we introduce that as a tautology and then do universal specification. In general, I would have just started with that, but just to show you guys once, that's what it looks like. Or we can think about Emma's approach. One, which is introduce the negation of it as a conditional premise that we promise to get rid of. Let's look at not C of x plus x prime plus x. So we'll do both approaches. We'll follow through one and then go back and do the other. Okay. So, sticking with this approach for a second, what can we do now? Remember where we're trying to get. We're trying to get to C of x plus x prime plus x. So I'm trying to get C of x plus x prime plus x. That's where I'm trying to get.
That plus x just doesn't fit in. Because none of the stuff.
All right, I'll give you another one.
You can't work
So I can switch this to C of x or not C of, not C of x plus x. That's using axiom 2.
That's what I was thinking of.
Okay, so there's our x plus x.
Where does the plus x come from? How do you get that in there?
We just got in there.
Is it
Like
less-
it's you can't modify terms.
So what's next?
That is confusing if you're saying that you're using the axiom 2.
So I used axiom 2. Axiom 2 says if you have C of anything, you have C of that thing plus anything else you want.
But that's implying that x and y could be different, and that one's implying that x and plus y is always the same. Or sorry, x plus x is always the same.
If it's true when x and y are anything, it's true when they're the same thing. This x here is not the same as that x there. They're just standing variables.
I know. Okay. That does make sense.
With the right side of your or, then you can get C of x plus x prime.
So we can rewrite this as, that marker is really dead. That's not much better. So we have C of x or C of x plus x all primed. She's saying we know that because not C of something is the same thing as C of that something primed. Not C of something gives us C of that something primed.
I kind of just want to use A2 again, like the same way you did before, but I don't know. Just add a plus x.
We need something that combines them together.
Yeah,
Into
doesn't
one
mean
C
the left
function.
side, but that doesn't make sense to me.
So what do we have that combines them together?
RAA.
RAA? Oh, reductio ad absurdum? No, look at those and see if there's something that brings two C's together into one.
Are we talking about A5?
A5 does it, so we could use A5.
But there's no double plus.
But the one that I like more is theorem 5.
That does not even. Oh.
Oh, yeah.
So let's play with theorem 5 for a second. Let me write the contrapositive of theorem 5. Let's write the contrapositive of this. You with me? So not this implies not this. So not C of X and not C of Y implies not this, which is just C of X plus Y. You with me?
And then distribute.
And then distribute the not term. When you distribute a not over an and, it turns it into a or. So not that gives us just C of X. Or C of Y gives us C of X plus Y.
So why is it invalid to use A2? And just add a plus X to that C like you did before?
We can use A2 and add a plus X to this term if we want.
To the one on the right.
Add a plus X to this.
Is it saying for all terms X or for all variables X?
We can do what you're saying. So we can do this. 5. Now we have C of X or C of X plus X all prime plus X. That's valid.
Oh, but we still have the one on the left that we'd have to
Yeah.
do. So we still can do that to the one on the right. Okay, that makes sense.
So yeah, doing that isn't a valid step. It just doesn't really help us with anything.
Right.
On the other hand, what does this say? If I have C of X or C of Y, I have C of X plus Y.
Brilliant.
I think we need to change the order first, right? So first, use the fact that or is
Commutative.
commutative. So just rewriting this. Just rewriting this, we have C of X plus X prime or C of X.
Or C of Y.
And now we have C of something or C of something gives us C of those two things added together. So using theorem 5, we get C of those two things added together. X plus X prime plus X.
Is there a reason you wrote that in red?
No.
That's weird. That's
And now we can universally generalize.
yeah.
Okay. Or we could have done it the way that Emma was thinking. We could have started with not C of those two things. Okay, what does that give us?
Well, you could use theorem 5.
Yeah, we're going to use the same, basically the same exact logic we did. We're going to use theorem 5. Not C of those two things gives me not both those things added together. So theorem 5 gives me
That exact thing.
sorry, I have to be a little bit careful here. It gives me not C of X, not C of X plus X prime, and not C of X. Did I write that right? Using theorem 5.
Looks right.
Theorem 5 says if we don't have their sum, then we don't have either of them.
And is
If I don't have their sum, I don't have either of them.
commutative.
Huh?
whatever, yeah, it looks right.
Okay. Now what?
We can use axiom 4
Axiom 4?
on the left side of that end.
Axiom 4 on the left side of it. We have not C of something prime, just gives us C of that thing. So now we have C of just x plus x, and not C of x. Using axiom, what was that? 4. 4 says if you don't have C of x prime, then you have C of x. If you don't have C of x prime, then you have C of x. Okay? Now C of x plus x implies
C of x using theorem 4.
using theorem 4.
Oh, and that's by way of contradiction.
It's by way of contradiction.
That's what we're trying to figure out, like, what the heck is it got?
So we have x plus x, and we know not x, therefore we know C of x. So from this we get C of x
Back and forth.
from theorem 4. And so now we have C of x and not C of x. Contradiction. Therefore, this statement can't be false, so it has to be true. So therefore we have C of x plus x prime plus x.
That way was easier.
Was it? Or was it you just got used to logic one way and then the other way became easier? Because they both use the same logic going through theorem 5.
Yeah.
I guess one we had to use theorem 5 in the contrapositive. So yeah, maybe this was easier because we could use it directly.
Of course.
But the crux of both proofs was realizing, oh, you use theorem 5.
Yeah.
But yeah. Okay. And then theorem 9. Oh, theorem 10. Theorem 11. Maybe we'll skip over those two. Because they're a lot like theorem 9. Same kind of trick. You either need to start by assuming something like this, or you assume they're false and it gets to some contradiction.
For every proof of contradiction, can you like do the left-hand version of it, like that you did on the left side?
Could I always do it this way instead?
Yeah.
I assume so, but I'm not positive. Because to prove, when you prove proof by contradiction, when you prove that that's a valid rule, because it's a rule that we prove, reductio ad absurdum, you use the law of excluded male to do it. And this is using the law of excluded male directly.
That's why I thought it would be the case, but I'm not sure.
So it could be the case. I could see how it's probably the case. I would guess it's the case, but I'm not positive. And in math, this is a far more common approach than this is.
Yeah, it seems like that's easier to reason about.
A lot of times it's a lot easier to reason about.
So I said,
So, might feel more natural to do it that way. Okay. 10 and 11, similar proofs. I don't bother writing them all out. Let me look down here really quick to see if there's anything interesting. Yeah, pretty much the same thing. Because I was going to do 10 again that way, and then 11 I was going to do proof by contradiction to show that we can go either way. But we saw them both in one go, so I think you got it. Okay, so there we go. There was our second axiomatic system. Now I told you I'd give you intuition for what on earth all this gobbledygook means. So I'll give you an actual interpretation. So you can interpret C is the predicate is true. So it's saying whatever you give it, X is true. That's all it's saying. Prime is the same thing as not, and plus is the same thing as or.
I do that.
I do not understand how prime and not is the same thing, right? I don't get how you can input, or if you, okay, so the prime input is equal to not the input.
What I'm showing you here now, I'm not saying that this is what they are. I'm saying here's a valid interpretation. For all these crazy symbols, I could, you gotta go? Alright. For all these crazy symbols, I could have done the interpretation C is a predicate is true.
Okay.
Right? So I defined C, so it's a predicate that operates now on Booleans. Things are either true or false. So now I can define prime in terms of the Boolean operator, not, and I can define plus in terms of the Boolean operator, or. And it's a valid interpretation.
Okay.
What do we mean by a valid interpretation? If you interpret the axioms this way, all the axioms will be true. And therefore, all the theorems will also be true. And so we can read through it. What's it saying? For all x and for all y, if it's true that you have x or y, it's true that you have y or x. What's this one saying? For all x and for all y, if it's true that you have x, then it's true that you have x or y. Yes, that works. This one is saying, if it's true that you don't have x, then it's not true that you have x. If it's true that you don't have x, it's not true that you have x.
Okay, so why is it that x prime means that?
It doesn't mean that. I'm saying this is a way that these symbols have no meaning, except for what the axioms give them.
Oh,
This is an interpretation we could give them.
I see.
The same way that Q up here doesn't mean anything. The interpretation, it means what the axioms give it meaning, but that's it. I gave you the interpretation of Q, we can think about it as meaning weakly preferred.
So this is an exercise where we switch out variables for other things, switch out the symbols that could technically mean other things, just so that we follow the rules and that the rules work.
So we often in mathematics, when you get to deeper into mathematics,
Okay.
you find these abstractions, these rules in a system like this. And if you plug in those rules one way, then it's like you're doing arithmetic on the real numbers. And if you plug in those rules other ways, it's like you're doing some algebra with vectors instead. And there's some common rules that both those systems seem to be using that at first glance seems like are pretty unrelated systems. And then there's actually these fundamental abstractions that it turns out one's just one interpretation of these abstractions and the other's just another interpretation of these same abstractions.
Yes.
So if I work with those abstractions directly and prove things about those abstractions directly, I'm indirectly proving things about two systems at the same time. And maybe there's a third system out there that abstraction also applies to. So it's a very powerful thing to do. To abstract away from a bunch of systems, just fundamentally what it is, some fundamental components about it, and then prove just using those fundamental components.
Yeah, that's cool.
And then in the special case, where C happens to be this, prime happens to be this, and plus happens to be this, you get all these theorems for free. We don't have to recheck them.
Yeah, so I can see, like, for instance, if you put,
Yeah, let's just keep plugging through each of these to make sure it appeals to your intuition.
yeah,
So this one says, if it's true that you don't have x, then it's not true that you have x. This one says, if you don't have not x, then you have x. This one says, if you have x or y and you don't have x, then you have y. If you have x or y and you don't have x, then you must have y. All right, what does this one say? If you don't have x, then you have not x. What's this one saying? If you have x, then you don't have not x. What's this one saying? If you don't have x or y, then you don't have y or x. What's this one saying? If you have x or y, and you don't have x, then you have y. Notice that this one and this one, we're saying the exact same thing, basically. Which is why this is all we need for this.
that's cool.
What's this one saying? If you don't have x or y, then you don't have x and you don't have y. What's this one saying? If you don't have x and y, then you don't have x. If you don't have x and you don't have y, then you don't have x or y. What's this one saying? If you have not x, then you have x.
Yeah,
And this one's saying, if you have x And if you know x is true, and you know either x is false or y is true, then you must have y.
That's not likely.
Yeah, this one sounds weird. This says x is false or y is true.
And we know X is true.
And we know x is not false.
Yeah.
So y must be
X is
true.
Okay.
That must be false.
Let's say it again.
X is
Think about it this way. This says x is false or y is true.
Oh, X is
But x is not false. X is false or y is true. But x is not false.
so Y is
So y is true.
Think of that. Okay.
Okay. And this one says it's always the case that x or x is false or x is true.
Yeah.
Yeah, this is the exact same thing as saying x is false or x is true. And this one is saying y is false or x or y is true. Because if y is true, this whole thing's true. And if y is false, that's true. So you always have that's true or that's true.
Which that's true. Yeah.
And then this one says x or y is true or x or y is false. Which is true. X or y has to be true or false. So there's one interpretation for this system.
That's cool.
There we go. We just did our second axiomatic system. And we didn't really get into interpretation. That took longer than I thought it would. Shoot. But it's a good example to go over.
Oh wow.
Yeah, I can't believe it's already 9.
I didn't even notice that word.
I wanted to say one thing briefly about interpretation, and then we'll restart with this next time. So we gave you one interpretation up here of what these symbols could mean.
Yes.
Now I'm going to give you another interpretation.
Oh boy.
And the interpretation is, I can replace q there with less than or equals. Or sorry, greater than or equals. So axiom 1 then becomes, ignoring the quantifiers, I'm not going to rewrite out the quantifiers for the sake of ink and time. Says x is greater than or equal to y. If x is greater than or equal to y and y is greater than or equal to z, then x is greater than or equal to z. Right?
Yeah.
That's true. Let's look at what axiom 2 says. Axiom 2 says it's always the case that x is greater than or equal to y, or y is greater than or equal to x. Is that always the case?
Yeah.
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 And then definition, this definition is just defining a new symbol. We'll define a new symbol too. We're going to say it means x is equal to y, is logically equivalent to, x is greater than or equal to y, and y is greater than or equal to x. If x is greater than or equal to y and y is greater than or equal to x is equal to y. Similarly,
Oh, I get where you got this all from. Yeah.
I can replace preference with greater than. X is greater than y is logically equivalent to. It is not the case that y is greater than or equal to x. If y is not greater than or equal to x, y must have been less than x. Or in other words, x is greater than y. And now we can go through all our theorems that we proved last time. We only have the first one here. But we can go through all the theorems that we proved last time and just replace the symbols and they're still all true. We don't need to reprove them and see if they still work with these new symbols that we came up with. We prove that they're true under every interpretation. As long as we come up with things that we plug in that make all the axioms true and the definitions still work, then all our theorems are still going to be true in that new interpretation.
I see that.
So I give you two different interpretations for the exact same axiomatic system. All the theorems still follow. Because we didn't rely on any interpretation when we proved it. We just used exactly what the system gave us, nothing more, nothing less. Here we just used exactly what these axioms told us we could do. And nowhere in all these proofs did we ever think about what C actually meant, or what plus actually meant, or what prime actually meant. We just used what the axioms gave us. Make sense?
Yep.
Good. Because getting that down is the hardest part about getting down axiomatic systems, which is the hardest part about getting down math. Once you get comfortable with one axiomatic system, you pretty much get comfortable with math. In all different fields of math, it's just jumping around to different axiomatic systems. If we replace these 5 axioms with Euclid's 5 postulates, now we're in a field called geometry. And that's what geometry is. It's the field you get when you start out with Euclid's axioms. If we replace it with the axioms of arithmetic, now we're in arithmetic. If we replace it with the axioms on the real numbers, now we're in real analysis or calculus. If we replace it with the axioms on complex numbers, now we're in complex analysis. All the different fields of math, they're just different axiomatic systems. And the field you're in is dictated by the axiomatic system you're using.
That makes sense.
That's what all math is. So that's why understanding this stuff, great for understanding the foundations of math. So we'll end it there and re-pick up next time with interpretation.
Okay, thank you.
Yep. Can't believe we didn't get to that board.